So hello everyone, welcome back to the another lecture. So my name is Ashish and today we will see the closed loop MATLAB simulation of the DAP converter using the single phase shift modulation. In the previous two classes, we have talked about the open loop simulation of the DAP converter using the single phase shift modulation. And I hope so you understood how we have implemented that and how the power is transferred in single phase shift and how to calculate the parameters of the DAP converter when operate in the single phase shift, how the value of the inductor influence the overall power transfer capability, and how to generate the phase delay delta for in between these two bridges. So this part we have seen. Now with this in this video we are going to understand how to implement the closed loop MATLAB simulation. So first thing you need to understand what is my controlling objective. Like in when we have done it in open loop, what is my controlling objective is my output V0 should be constant. Then when we go in a closed loop simulation, again now if I am implemented in a single phase shift, my controlling objective will remain the same, my V0 should be constant. But why there is a double phase shift, why there is a triple phase shift, then if I have my different phase shift, then my controlling objective should be changed, okay, or my controlling objective should be more than one. So what are those and all, that part we will see. Then what are the different controlling methods available if you wanted to do the closed loop simulation. Now for single phase shift, what are the different method people have used, implemented, that we will see. And then we will go with the very simple closed loop method, that is the cascaded control, which is a well-known method people have also implemented, and how to implement and all, that part we are going to cover. So with this I will start this lecture. So before going to the actual simulation part, I wanted to discuss one point about the soft switching. That point quickly we will discuss, and then we will go next again on our closed loop simulation. Why I am discussing that point of the soft switching is I am going to make a video next to this about the soft switching, where we will understand the soft switching in very detail, like how the soft switching happen. Even if you know, I am pretty much sure that you will understand something new from those videos. But I wanted to make one point. Just for that I am going to discuss what are the reason of soft switching when operating a single phase shift. Okay, so first I will cover that, and then we will come to the closed loop MATLAB simulation. So let's jump on to the new window. So here we are on the new window. Now what point I wanted to make is, now this is my DAP converter. When I operate this DAP converter using a single phase shift, there is a certain reason where if you operate your DAP converter, then only you can have the zero voltage switching. So I am assuming that zero voltage switching, zero current switching, you know, these are the part of soft switching. Okay, so even if you don't know, just try to keep this particular point in your mind. Just for some time in next video we will understand everything in detail. Okay, so what I wanted to say, when the DAP converter is operated with the single phase shift modulation, there is a certain reason inside which if you operate, then only the soft switching will achieve. Now this is that particular reason what this curve indicates. So this is my D, here mentioned as the delta, but this is my D, which is come from 0 to 0.5, and we know that at 0.5 we will get the maximum power. What is this M? M is nothing but the V2 by V1 into N1 by N2. Now I said you that N1 by N2 parameter we have fixed. Okay, once we select some system, once we select and we design the transformer, we have N1 by N2 fixed. Now V2 by V1 and I have also told you that this is generally we take 1:1. Again V2 by V1 for our open loop simulation is 800 by 800, and it is 1 by 1. So my M value is M. So at M is equal to 1, I have the entire reason to operate as a zero voltage switching. But what if I will change this particular V2 by V1? So this M value will shift somewhere upper or somewhat lower. Then that time this D value is very important, like where it is going to be operated, and this will degrade the performance of my DAP converter. If it is goes in this particular region or this particular region, my DAP converter will don't show the zero voltage switching, and because of this efficiency will degrade, losses will be more across the switches. Okay, so it is very important that at what particular range you are going to operate your DAP converter, and that accordingly you are going to wisely choose the N1:N2 ratio, so that you should lie inside this particular range when you go for the any implementation. Because when we design the system, we have seen that last time what we have done, we have not changed the basically N1:N2 value, we have not changed the phase shifting angle. what exactly is changing when we are doing it in open loop? The L value. And we also understood that how L value influence the overall power transfer mechanism. So my power basically is degrading and all this part we have seen, right? So this M value is very important when we go for single phase shift modulation, right? So I hope so. This point you just keep in your mind. As of now, we will discuss this point in very detail. This discussion is only for those who have very much interested in to know what is the n1 is to value I should consider. Okay. But apart from this, this is just a small discussion I have done. This discussion I am going to do in next to next class in very detail. Okay. Even if you don't understand, that is perfectly fine. But just keep in mind, we need to operate in this area so that we can achieve the soft switching. And I am going to make a video on soft switching also using the Plex software, where in MATLAB it is not possible to show the soft switching zone, soft switching whether happening in the switches or not, but in Plex software I can show you that look, the losses across the switches when operating in this area is 0, and when I will go in this area the losses across the switch will be something happen. So those part I am going to show you in the Plex. Okay. So with this, I will now move to our actual video, which we have to learn in this particular case. What is that? How to control in the closed loop, right? So this is the a particular MATLAB Simulink model we have drawn in the last class, and using this particular small open loop control, we have control over basically we have generated the we know using the mathematics what this particular ratio constant will come, and that I am feeding to this T naught, and it will generate the phase angle between the two gate pulses, and accordingly my power will be transferred, right? Now this particular thing we need to generate using some controller, because every time if I wanted to change my input, if I wanted to change my output, I will not going to calculate this thing, right? So it should change dynamically, because I am not going to change my L value, I am not going to change my n1 is to n2 value. Once I have fixed this, then only this parameter should change, and it will govern my overall power transfer, right? So how to do that, that part we are going to see. So before going there, what are the objectives of controlling? So I will say that if I am operating in the single phase shift modulation, I have only one objective, which is my output V0 should be constant. So for making the V0 should be constant, I am changing the phase displacement angle between this input and output bridge. Now if I will operate it into the double phase shift or triple phase shift, what are my objectives? Now only having the one objective is not the case, because my output anyway V0 I am going to achieve. But why there is a need for double phase shift or triple phase shift? So what is the second objective we should have is this current through this inductor IL, because I don't want the current peak, I wanted to limit the peak current value, and for limiting this peak current value we will go for double phase shift and triple phase shift, because this peak current value in single phase shift may go to very high value, and that I don't want, right? So for that double phase shift and triple phase shift we have for the my second objective. Okay, but as of now we are implementing the single phase shift, and for single phase shift only single objective we have, which is my controlling the V0. Now how to implement that part we will see. Now there are some control strategies which we are going to understand. So when it comes to the controlling part, try to understand from very basics. Now I have one DAP converter, which is a DC to DC converter. Now if you have seen my playlist of how we can control any converter using the transfer function, there I have taught you about how to do the small signal modeling and all. Now for this particular converter, if I will do the small signal modeling and find out its controlling transfer function, then I have very easily I can control my output voltage, I can control my inductor current. What I need is controlling transfer function. So you understood about the small signal modeling. So in this video I am not going to go in detail about how we can derive the small signal modeling transfer function and what are the actual small signal modeling transfer function available. So I am going to give you some references. Using these references you can get the overall small signal modeling transfer function, which you can use when you go for further MATLAB simulation. My objective from this video is to show you what exactly the step we need to follow to have the closed loop MATLAB simulation. Okay, so these are the three papers. I have also referred them, and these are really good paper. So if you have IEEE access, try to download this paper and try to see how they have done the small signal modeling, and you will get the small signal modeling controlling transfer function. So one of the way to control this, maybe if you have seen my basically DC to DC converter playlist, where we have control using the cascaded control, voltage mode control, and different control I have explained there, right? So again, same aspect, same control we will use. Now in this video also I am going to explain you the cascaded control. So what actually I need is small signal modeling transfer function, but in this video I am going to make it through the error and trial method. That part also I am going to explain you how we can do it in using the error and trial, and we can come up very quickly with some PI values. Okay, so for controlling any, we need the small signal transfer function, and these are some references which I wanted to share with you. You can go to them. Okay, now again, what are the different? So small signal modeling is the something which is very important, and we have the small signal transfer function, then we can control anything. Okay, now for this controller, if I wanted to control this, so this is the very well known first control method which we are going to use, which is a traditional dual loop control for the DAP converter, and generally I have seen this method is employed. Now what this method do is actually, again, reference minus actual. I will have my reference output voltage which I am going to compare with my basically actual one passing through the PI controller. If I have my small signal model of the V0 by I, then basically I can easily tune it with this particular transfer function V0 by I. If I don't have, then I need to go with the error and trial. Then it will generate my I reference, which is the current which is going to be flow here. Then I will compare it with my IL average. What is the IL average? This is should be 0. Okay, IL average which will come actual, and this reference should be which is going to be generated, that is 0, because you remember the waveform of IL. What is the nature of the IL? It is sinusoid, obviously, so its average value should be 0. So it is compared with the actual mean value, average value of the I, and this is passing through my PI controller again. If I have my V0 by, if I have my I0 by D transfer function, D is my duty ratio, or in this case my phi, I0 by phi transfer function, then I can basically easily tune it. Otherwise we need to go with the error and trial. So what this particular block will generate? This block will generate the phi, and this phi I am going to give here. This phi I am going to give here. Okay, so this is the same thing which we have basically implemented in open loop. Now instead of giving this constant value, I am going to give some reference which is coming from my controller, and now this particular phi will change based on whether my input and output values changed. Okay, and based on that I have generated this particular signal which I am going to give to my second bridge. For the first bridge, I know that what is the phase what is the gate pulses pattern I need to apply for my primary bridge. So I am keeping the same thing. But when you go for double loop control, when you go for basically dual phase shift or triple phase shift, this pattern is also not fixed. So this pattern is also I need to control, and how to control that pattern, that is another aspect. So that is done through some lookup table type of thing, that also we are going to see in upcoming future videos. Okay, but as of now, for single phase shift implementation, this particular block remains the open loop. Only thing which is going to be changed is this particular block, and what exactly is changing, this ratio constant which we are giving as a constant value initially, now this is generated through one control aspect. Okay, so this particular control, and then I am going to give it here. So this is how overall we are going to implement my closed loop control. Okay, I hope so you understood this thing. Then few another controller also there which we are going to see, and I am giving you the references because we are just implementing this control. I wanted to show you that what is the limitation of this control, that part also I wanted to show, and how it is difficult to operate my DAP converter into wide input and wide output range if I will go with some error and trial values. Okay, if I have the exact transfer function, then it might be possible to operate in wide range, but how is it difficult when we go for some error and trial method? Okay, so that thing, all the things we are going to cover in this video. Now the another aspect, another method to control is basically just by observing the IL reference, and some predictive current controller is there, and it will generate my phi, and that phi I am going to give here. So this is the another method. So if you wanted to understand how the predictive current controller is happen just by observing this particular value, there is a paper, very good paper, that is digital predictive current mode control for the single phase high frequency isolated transformer dual active bridge DC-DC converter. You can refer this paper, you will understand how they have implemented it in detail. Okay, so this is another basically another controlling method which we can use, but in this video I am going to explain this one only. Another thing, if you wanted to charge suppose battery instead of this resistive load here, if you have battery in this particular side and if you want to do the battery kind of simulation, like you have bidirectional kind of simulation, then you can use this particular control. So what it is doing, it have the battery parameters like my what is my battery voltage, actual battery voltage, reference battery voltage, actual battery current, reference battery current, passing through the voltage controller and current controller, and then it will select the mode whether it is CC or CV, and it will generate the phase shift. Okay, and that phase shift is given to my S5 to S8 bridges, and S1 to S4 bridges we already know how the gate pattern is look like in a single phase shift. Okay, so if you wanted to understand exactly how the battery is charged, how this particular method is implemented, so I have one separate video which I have made on DC to DC converter battery charging. Okay, so that is for buck converter, not for the DAP converter, but if you watch that video you will understand that how we will basically get the values of this voltage controller, current controller, how to select the modes, and then how it will there I am going to generate the duty ratio, but here what is our requirement to generate the phase shift unit. Okay, so that is the only difference, but you can refer that video as well, which is available on my channel. Also, if you wanted to understand how this particular block diagram is basically implemented, you can refer this particular paper. This is again very good paper, I would say. So at least you will get fundamental idea, because most of you, those who are watching this video, I guess they wanted to implement bidirectional DC to DC converter, right? And they are using the DAP converter. So how to implement, and your maybe targeted application is EV or charging application. So for that you have to implement some modes. So all these things are there, you just need to understand some basic idea how we are going to implement, and then you can go for advanced topics. Okay, so I hope so you understood from this particular a small discussion, like what is this particular soft switching zone, that is over. Then what are my objectives when we go for single phase shift, how my objectives are modified when we go for double phase shift, triple phase shift. Again, what are the control strategies? So small signal modeling is very important, and you can learn the small signal modeling from this particular papers. Then in this video I am going to implement this particular thing using some error and trial method, and what are the some different methods are available, that also we have seen. Now I will jump to my MATLAB window, and there we will try to run the MATLAB simulation and see how exactly the things are happening. Okay, so let's jump to the MATLAB window. So here I am on my MATLAB script. So the same MATLAB script which we have used and open loop simulation, the same MATLAB script I am using here as well. Now what basically parameters? So here the method which we have used for calculating the value of the L and basically C are approximate, because when we go for dynamic calculation my V1 and V2 might change. So these things also we need to take into the account. Only going for the value which is for constant value of L, like for V1 constant, V2 constant, I am going to design my L value. But when we design the value of L and C for worst case, like what is my range of the V1 we should consider, what is the range of V2 I should consider, there is a something long process which we need to follow to calculate the value of the L and C as well. Okay, so that thing also you can find it in the papers. If you need, I am providing, I will try to provide this. Okay, but as of now what I am going to show you how to implement the closed loop implementation. Now with some constant values of V1 and V2 and some my fixed power output and switching frequency and my turns ratio, again I am keeping as 1:1. I have tried to calculate the every parameter. Now you know what is the inside the script, so I am not showing it again and again. So I am getting some phi value, but this phi value I don't need as of now, because this phi value I will generate through the controller. If I am going to do it in open loop, that time this value is needed, but as of now I don't need. So what things I hope so you understood this script previously, so I am just scrolling it down. If somebody is watching this, just please watch the previous video. I have explained this scripts as well. Okay, how we have derived of all the formulas and all. Okay, so now this ratio constant is come. What is the time which is come for the, what is the phase time comes, that is 1.38. So my controller which is trying to provide the output, this should come nearly equal to this particular value. If this value will come, then my overall power transfer will be happen properly through the controller. Okay, what is the value of the L which came here? So L value is again 2.13 e minus 5. Okay, so for my this particular parameter of v1 v2 power fs and n, I got the L value as 2.13 minus 5 Henry. Now what I am going to do, I will, with this value of the L, I will keep the value of the L constant. I will run the simulation first. Then what we will do, we will change the value of the v1, we will change the value of the v2, and we will try to see whether my controller works perfectly fine or not. So now let us jump to the Simulink model, and then there we will do everything. So here we are in our Simulink model. Now we will try to understand some few basic things first, and then we will move forward. So now here I have keeping my amplitude at 800 volt. Now I have keep it at 800 because I have not keep it at V1 because I wanted to change this. How I am going to change this? Because I wanted to show you few more result with a different value of the V in, and I don't wanted to change the value of L as well as N. So that is why I am manually feeding this value. Then what is my value of the L? So L value which is calculated, same value is here. What is my turns ratio parameter? You just see. I am not explaining the each block because this part we have seen in the open loop simulation. So my ultimate objective is to show the closed loop simulation. So that is why that is more main focus. So 30 kilohertz my power transfer, 100 kilohertz as my switching frequency. My input output I have keep it as 1:1. Magnetizing inductance very high value. So this part you already know. How to do the arrangement and all that part you already know, just to make a bridges. Now my capacitance value, that is also I have keep it as some C into 2 something, I have that also I have told you, and my R load the same which is calculated. Okay, now how to do the closed loop, that is also we have seen, just again one time we are going to see. So for my input side bridge, I have the same phase sequence. So I have my this pulse generator block which will generate the 50% duty ratio, and S1 and S4 will operate at the same time, and S2 and S3 are operate at the complementary to S1 and S4. So this thing we know, and whatever signals are there that I need to phase shifted, which we are going to phase shift by the variable time delay block, and then those phase shifted signal I am going to give to S5 and S6, S5 and S8, and complementary of those I am going to give to the X6 and S7. Okay, so this thing already we know. Now only thing I have changed here is this phase delay. So I have keep one block which is coming from the controller, that is my phase delay block. Initially we are keeping it as a constant. Now how this will come? So for that I have just implemented one simple controller here. So my reference output is 800 volt, compare with the actual V out. This is passing through an PI controller, and basically what I said, this PI controller will generate what? It will generate my IL average and reference, which is comes to 0, and this I am going to compare with my IL mean. So where is my IL mean? So this is the current which is going to flow through the inductor. I have taken the mean branch, so you know how to take the mean block. So mean block is there, and it will give my mean. So there are one more point I wanted to say, just I remember that it is not only the way to compare using the mean block. So people have tried to basically go here with the peak value as well. Okay, so there are the paper where you can see that somebody may find out the paper and he will ask, sir, people have used the peak value of this particular current and then they have compared. So that is also the another way, but that time you have to tune your PI controller for in that respect, because you are comparing with the peak value and then passing through the PI controller. So that is another way. Okay, now here what approach we are using? We are using the IL mean. So I am using the average value, and then I am comparing and then passing through my PI controller, and it will generate some phase delay, and that phase delay I am going to give here, and then this particular block will generate that appropriate timings. Okay, so this is what we are going to do. So I hope so you understood the things. This is the output where we are going to see whether my output is coming or not, everything. Okay, so maybe we have taken a bit of more time, sorry for that, but I just wanted to be very clear what we are doing. So the phase delay block, okay, and this is the very basic control. Now you are interested in what is the value of this PI, right? So I am just opening this. So how I got this value, maybe if you have watched my video previously, start with some initial guessing 0.1, 0.1 both the value, and then try to observe the output voltage response, and based on that you can just slightly modify the value. So what I said, start with very less value 0.1, 0.1 or 0.001, 0.001. So these are the initial guess value, and then based on the how your output is, basically you will just slightly modify the value, and you will achieve. So this is a error and trial method, and but it will also effective, but only issue is it will not achieve your required phase margin and gain crossover frequency. So maybe for some particular value this error and trial method value will works, but if you change the system parameter this value might not work. Okay, that part also we are going to see. And then for another block, so for this start with this particular block, what you will do, this current controller block you fix some values like 0.001, 0.1, this value you initially fix, and then play with this particular values on T. Okay, and try to increase the kp value slightly, or maybe decrease the kp value slightly, so that you can achieve your required output. And based on here you can see that for what value of the kp, whether I need to increase the value of the kp or whether I need to decrease the value of the kp, that you can observe. Now I have keep the parameter. So once you are going to design the controller, you have to use the small signal model method only to get the accurate values. Otherwise what will happen, I will show you. I have make it for 800 volt. Now maybe the system will work, but if I will change the value the system might not work. Okay, so that is the issue with the error and trial. But anyway we are learning how we are going to implement the closed loop, how to get the value of the pi controller. Maybe we will learn in the next class. We will come with the very accurate model, exactly those will work for some particular range. So that part also we are going to see. Now I will run the simulation and we will see the results. Now for the 800 volt input and 800 volt output, and with the other parameter as it is, I am running the simulation and let us see what will happen. Okay, so based on that we can understand what is my output requirement. So let us see, observe the output voltage, whether I am going to get the output voltage as 800 or not. So you can see that the system is trying to reach to some value, but it is very slow. What it implies that my integral is basically less value. If I will increase the integral value, the system will be very fast. Okay, so that is the concept. Now it comes to 795.9. So I am fine with it. I need 800, but I am not reaching because I need to tune these particular values a bit of more accurately to get the exact result. But my main objective here is to show you. Okay, so this is how we can implement and you can achieve the required value. Now just see the waveforms bit of, and then we can move forward. So now you can see that it has taken some value because its kp value taking it towards the 800 volt, but its integral value is very less. So that is why we can increase the integral value so that this response time will be faster. So this is how we will tune in error and trial method, just by observing what is happening in the system. When we go for hardware also, generally we will try to use this method. We will see whether what kind of nature I am getting, and based on that we will just adjust the kp and kl values slightly. Okay, so I am coming at nicely 800 volt, and my basically output is also coming at nicely. But some you can see that some issues I am observing here, like some glitches are there. These glitches are because of the controller, because controller is not that robust or not that optimized well, and because of this kind of issue will persist. Now just let us try to see the few more waveforms, whether my current is coming nicely or not. That part we will see. So here again I can see the glitches, and these glitches are there because of the control action. Okay, so that is why I told you that controller tuning and basically having the controller robust is really a tough challenge when you go for isolated type of the topology. So okay, I'm getting control basically current response also nice, but in between there are the glitches. Now where I am interested, okay, with this some particular values I am reaching nearby to my output voltage of 795. Now try to observe if I will change my input. Now it is 750, I will make it from 800 and try to run the simulation. What will happen? So these are error and trial value. Okay, if you tune this value using the small signal transfer function, then might be with the 750 value and keeping the rest of the parameter of the system same, I might reach the output voltage of 800, but whether I am going to achieve here or not, that we will see. So now at what particular value I am reaching here? I am reaching here nearby about 775. Why? Because although my values of the Kp and Ki in both the are somewhat I have tried to tune using the error and trial, but still this controller values are not capable to make my system nearby 800 volt. It has stuck nearby about the 776. Why? Because controller is not working, or I would say the bandwidth of the controller, because when we tune the controller using the small signal modeling, we will see its bandwidth, we will see its gain crossover frequency, phase margin, everything we will see, and based on that we judge the stability whether at this particular value my controller will work fine or not. So all these things we need to taken into the account. Now you can see that this value nearby comes to 799 801. How it is happen? Because maybe after some time my controller parameter try to adjust them, like this overall response of the system, and it will try to make it nearby 802, but it has taken more time, and that I don't want, because my system switching time from one transition to another transition should be very fast. And here I am just doing the control in closed loop, but I am not changing the dynamically my input. I have started with the 750, but it will take a really a long time to reach to 750. So that is why I am saying that it is really important how you tune the controller. So controller tuning is a really important task. Again we will see the waveform, so you can see the waveform how the glitches are there. Okay, but it will try, controller try to go as much as possible to nearly 800 volt. Okay, but this is how a control action works. Now if I will change my input to very large value, let us say I wanted to operate for 400 volt to 800 volt. So now I am operating it from 400 to 800 volt. Let us see whether I am getting the response or not. So I just wanted to show you few things, so that this thing we have not seen, right? Whether my time generated is properly matched for 800 volt 800 volt input, 800 volt output. So but I'm pretty much sure that this time is matches to what we calculate theoretically. Now here you can see and observe the output. My output is now 40 volt 50 volt, so my system is completely collapsed. So what is happening with this control parameter, I will never reach the 800 volt. Now it is going somewhat 350 400 volt, but whether I am going to reach to 800 volt, no, that is really difficult with this control parameter. So maybe if I will wait for a long time, my controller action will happen in such a way that it might take it to 800, but it is really difficult, and I don't have that much of time to wait for my system to run so much. Okay, so with this I will just try to show you for output as well. Let us make this as 800 volt and try to change my reference output. So let us say I will make it as 750. So maybe for 750 it will work, but if I will change it value bit more further, it will not work, because even when we design the accurate closed loop transfer function using accurate model, and when we tune this pi value, we have some particular range. We can't say that my controller will work for 100 volt to 800 volt, or you have to make in a system in such an adjustment that with changing the input, system should adapt the change. System should know that okay, my input has changed or my load has changed, my output has changed. Then I can choose the values of the kp and ki from some basically lookup table. So for this particular output voltage I should have this value of the pi, for this particular output voltage I should have this value of the pi. So that provision you can keep when you design the closed loop control, okay, in DSP or FPGA. But if you think that okay, only having one particular value I will run my system and every time it will work, that will not possible. Okay, so that is why people move to some model predictive control or adaptive control, because there you don't have to play with this kpki value. It is really difficult to go with the kpki value and always get the desired output. Now I have keep it the 750. Whether I am going to get the 750 or not, just we are going to see once. So now it is going to 770 760. You can see my reference is 750, right, and it is coming nearly about the 761. So my based on what is my desired output, I am not getting the exact response. So why these things are happening? Just because of the controller. So try to go through those paper, try to learn the small signal modeling and try to model the system. If you don't know how, after having the small signal model, how to tune the controller, then you can watch my DC to DC playlist. There I have in detail explain that how we can process step by step for controlling, okay, when we have the small signal modeling transfer function. So for this video I am done with this. Okay, I hope so you understood that how we can implement the closed loop control, what are the objectives which we have, and how important it is to tune my overall particular controller. Okay, now in the next class maybe I will go with the basically small signal modeling approach if I feel there is a need, or we will go for the soft switching in the DAP converter, because I wanted to explain you how the soft switching happen. I wanted to teach you few more different concept about the soft switching which are generally not known to the people. Again, then we will see in the plex how the soft switching happens. So next 2 through 3 video I will make on the soft switching in the DAP converter. Okay, and then we will move to the next modulation scheme. So with this I will conclude this lecture. Thanks for watching. Maybe if you feel this is slightly lengthy video, that is also fine, but I must teach everything what I know. Okay, but I'll be happy if you comment out about how this overall video is, and thanks for watching.